Welcome to the lecture's next part. This second episode of the lecture about Euler's number deals with the way to arrive at the value of e. As said before, a power series for e to the x must be set up, but this will appear not to be so difficult as it may seem. Instead of the Taylor series expansion method, that would be the normal procedure for setting up a power series, in this specific case, quite an easier way can be followed. This will be done in the form of an iteration procedure, starting from the definition of e to the x that resulted from section 1, namely that the derivative of e to the x is identical to itself. Eventually, by substituting 1 for x into the resulting power series, the number e will be found with high precision. The convergence behavior of the series will be paid special attention to. From a worked example of a real-world system, the importance of the number e for the scientific world will be illustrated. Prior to starting the iteration procedure, an initial estimation for the series is needed. For that reason, a tangent line is drawn to the graph of f of x equals e to the x at x is 0, where the function value f of x equals e to the 0, which is 1. Since the derivative of e to the x is supposed to be identical to the function itself, at this tangent point where f of x equals 1, it must be 1 as well. That means that the directional coefficient of the tangent line should be equal to 1. This tangent line, designated as f prime of x, that crosses the point with coordinates 0, 1, while having 1 as its directional coefficient, can thus be described by the equation f prime of x at x is 0 equals 1 plus x. By now, we know the starting point for the procedure to set up the power series for f of x equals e to the x in full. It consists of two elements. Firstly, the derivative df over dx must be identical to f of x itself, and secondly, in the vicinity of the tangent point, where x is close to 0, f of x is approximated by its tangent line f prime of x at x is 0. It is described by the equation 1 plus x. That tangent line, f prime of x equals 1 plus x, serves as the initial estimation for the function f of x to be set up. From that, the derivative df over dx is calculated, which of course equals 0 plus 1, since the derivative of 1 is 0 and that of x is 1. However, when comparing that derivative to the current estimation for f of x, the both of which should be identical according to the requirements, we notice that the term x is missing. At this point, the iteration procedure is entered, consisting of two steps that will be looped indefinitely. 1. Complete the derivative with the missing term from the current estimation for the function, and 2. Extend the function with an appropriate term that is needed to have the derivative completed. In step 1 of the first iteration loop, the derivative df over dx is completed with the missing term x. To allow for it, in step 2 the function has to be extended with the term x squared over 2. In the inserted box, it is shown that the derivative of x squared over 2 is indeed x. In the second loop, the function's derivative is completed again with that term x squared over 2, for which reason the function must be extended with x cubed over 3 times 2. Once more is shown that the derivative of x cubed over 3 times 2 is indeed x squared over 2. In the third loop, the term x cubed over 3 times 2 is then again appended to df over dx, and f of x is accordingly extended with x to the 4th power over 4 times 3 times 2, which at its turn is appended to the derivative in the 4th loop, and so on. The result is an infinitely long power series. The denominators of the successive terms are now explicitly multiplied by the factor 1 to make evident that these can all be expressed as ascending factorials. By doing so, the series can be compacted to 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, etc. This allows the power series for e to the x to be written in short as 1 plus the sum over x to the nth power over n factorial for n ranging from 1 up to infinity. Expressing the term 1 as x to the 0 over 0 factorial, using the less well-known fact that 0 factorial equals 1, allows it to be included into the summation as well. Therefore, the most compact formulation of the power series for e to the x is the sum of x to the nth power over n factorial for n ranging from 0 up to infinity. For an infinitely long power series to possess a distinct summation value, it must converge. That means that from a certain term on, the value of the successive terms have to diminish quickly enough for the sum never to exceed a certain value. To get an idea of the convergence properties of the power series for e to the x, term n is compared to its predecessor n minus 1. This shows that every next term equals x over n times the previous, in which x is constant, but n is ever increasing. Irrespective the value of x, there's always a point where it's surpassed by n, causing the multiplication factor x over n to become much smaller than 1, as soon as n is high enough. From that point on, every next term becomes much smaller than its predecessor at an ever-increasing rate. Although this is of course not a proof in a mathematical sense, it does make obvious why the series converges and why it does so at such rapid a pace. So, the reason of this fast convergence is that a factorial will eventually always outrun an exponential function. This is illustrated by comparing its successive values for n up to 10 to those of, for instance, the exponential 4 to the nth. The latter may have a head start, but in the end the factorial clearly gets the upper hand very quickly. At n equals 20, for instance, the ratio between the two has already grown to over 2 million. A nice illustration further is the comparison of the function e to the x to the polynomial that's obtained by evaluating its power series up to a certain length. When n is restricted to 1, that's when only the terms 0 and 1 are taken into consideration, the tangent line is reproduced that was the initial estimation when setting up the series. Of course, this will only approximate this function in the immediate vicinity of the tangent point. The match becomes better when the parabola of term 2 is added and is further improved by the cubic term 3. For n ranging up to 8, both curves correspond nicely, at least visually, in the whole of the horizontal range of x between -1 and +1. The value of Euler's number e is now found by substituting x is 1 into the power series, turning all numerators into 1. That means that e equals the sum of 1 over n factorial for n ranging from 0 up to infinity. The process of obtaining e's value is now shown by tabulating the successive values from evaluating the series for e term by term. By highlighting the decimals that obtain their eventual value, the convergence progress is nicely visualized. This reveals that from n=4 onward, roughly 1 additional decimal of accuracy is contributed by every next term of the series. As a result, the convergence process progresses quite rapidly, achieving a 15 decimal accuracy with 18 mere terms. To give an impression of what such 15 decimal precision of e actually means, 1 unit over the 15th decimal compared to e's value of some 2.72 is roughly equivalent to the 50 micron thickness of a human hair compared to the average distance of 150 million kilometers between the Earth and the Sun. You may wonder, why is the number e so important for many exact sciences like engineering? Well, that has all to do with its property that the derivative of e to the a times x power with respect to x equals a times the function itself. The time-dependent behavior of linear systems is namely governed by differential equations. That applies as well for nonlinear systems as far as they can be considered as linear under suitable conditions. Such linear differential equations describe a relation between a number of time-varying system variables fi of t and one or more of their derivatives of any order, like dfi over dt, d2fi over dt squared, and so on. The natural candidates of the solution to such differential equations are of the form a times e to the st, because their derivatives are proportional to themselves and are actually s times as large. Likewise, the second derivative is s squared times as large, etc. The number of possible terms depends on the order of the equation, that means the highest derivative in it. The constants ai and si, respectively defining the magnitude and the time behavior of such candidate solutions, are found by working the differential equations after substituting those candidate solutions, while taking the initial conditions of the system into consideration. The behavior of the system as a whole is then described by all individual terms combined together. Of course, this will all be experienced as pretty abstract for many of the viewers. So let's illustrate it with a simple example, a first-order electrical RC network, not driven by an external input signal. Equivalent examples can easily be found for other fields of science like mechanics, chemistry, and so forth. Via a switch, the charge capacitor C is connected to resistor R. The voltage across this resistor forms the system variable V of t, the behavior of which we want to investigate. Initially, the switch is open, but at time 0 it is closed, connecting the capacitor to the resistor. Notice that the RC product is designated as the system's time constant, the dimension of which is the second. Its value is arbitrarily indicated somewhere along the time axis in the graph below the circuit. The precondition of the experiment for negative t is that the switch is open while the capacitor is charged to the initial voltage Vc0, the size of 10 volts. As long as the resistor is disconnected, the output voltage V of t remains 0. However, that changes abruptly to 10 volts when the switch is closed at t is 0. This forms the system's initial condition. After that, the capacitor is discharged by the current I of t through the resistor, causing the output voltage to decay exponentially away over time. As soon as the switch is closed, the circuit's behavior is governed by the differential equation RC times the derivative of the output voltage with respect to the time equals the negative of the output voltage. It's not difficult to set it up, but as electrical network analysis is beyond the scope of this lecture, we won't go into more detail, so you are supposed to take it as given. Since it's a first-order equation, only one possible solution exists of the general form V of t equals a times e to the st, that is substituted into the equation. Of this general solution, the coefficients a and s are to be determined. The substitution result reads Rc multiplied by the derivative of a times e to the st equals the negative of a times e to the st. Working the derivative leads to rc times s times a times e to the st equals minus a times e to the st, from either side of which the factor a times e to the st can now be crossed out. The result, called the characteristic equation, is rc times s equals negative 1. From this characteristic equation, the value of s follows immediately. S equals minus 1 over rc. In this first order case, there's only one value for s, but in presence of higher order derivatives, the characteristic equation would become quadratic or even of higher order, leading to as many roots for s. Our intermediate solution is v of t equals a times e to the power minus t over rc, of which the magnitude a is yet to be determined. To find its value, the initial condition is to be considered, and that is the situation immediately after closing the switch at time 0. By substituting t equals 0, the exponential becomes 1, having the whole of the expression reduced to a. This forms the initial value of v of t, that is equal to 10 volts. Now the full solution is known. V of t equals 10 volts times e to the power minus t over rc. This is valid only from the moment on when the switch was closed, so for t equal to or greater than 0. Prior to that moment, its value was stuck at 0. This second episode of the lecture about Euler's number comes to an end here by wrapping it up in this brief summary. The main issue of this section was finding e's value from a power series for the exponential function e to the x that was set up by a simple iterative procedure. This procedure was based on the property of e to the x that its derivative is equal to the function itself, in combination with the initial estimation formed by the tangent line to the function at x is 0. Next, the convergence properties of the resulting power series were reviewed, indicating that the series will always obtain a well-defined sum, irrespective the value of the exponent x. By substituting x equals 1 into the power series, the value of e was found to a very high precision from a reasonably limited number of terms. Finally, the importance of e for science and engineering was illustrated from solving the differential equation by which a simple real-world example is described. Please hit the like button if you find this video informative, and I hope you're interested in the next episode as well.